We were looking at an application yesterday, and people made really good progress on this. I was very impressed. So when you read through this, what's this saying? We're looking at a heat transfer problem. We're supposed to determine the steady state temperature distribution of a thin plate when the temperature, so I didn't make this thin plate, I guess. Thin plate when the temperature around the boundary is known. The figure represents a cross section of a metal beam. So so here's the cross section of the metal beam, right? It's like we cut through this metal beam with negligible heat flow in the direction perpendicular to the plate. Okay, so the heat isn't flowing substantially. Here's the direction of the beam coming out into the room, and then perpendicular would be up or side to side, right? It's not really flowing substantially in either of those directions. Not that any of this is super important to being able to solve the math problem, but it's kind of nice to just see how this applies. The temperature at a node is approximately equal to the average of the four nearest nodes, to the left, above, to the right, and below. Solve the system of equations below to find the temperatures T1, T2, T3, and T4. So those are our four unknowns, right? How many equations are we going to need to solve this system? We're going to need four. Good. So what'd you get then, for example, if we take node number 1, how do we take advantage of this idea that the temperature at a node is approximately equal to the average of the four nearest nodes? So how would I calculate the approximate temperature at location 1 at that node? And so I've got the nearest nodes, right, left, and up and down, would be that one, that one, that one, and that one, right? And if it's approximately equal to the average of those, well, how do I average those temperatures? Yeah, I just add them up and divide by 4. Okay, so then we end up with one of our equations being that. T1 is equal to the average of those 4 temperatures that surround it. For 2, I'm going to do the same thing for all 4 of those nodes. For node number 2, it would be node 1, node 3, 45, and 25, and so on. And I can just do that for all of them. And there are my 4 equations. Now, what could I do? Those are a little bit inconvenient, those 4 equations. What could we do to simplify those? Because ultimately, if we're going to solve this system, you think how we're going to solve this. I've got 4 unknowns and 4 variables. Can I solve by graphing? No, you can't graph something in 4 dimensions, right? So how am I going to solve this thing? I mean, we could do it algebraically, but thinking we want to do this a little more quickly. Yeah, we're going to solve this using a matrix, right? And you guys already know the trick to let technology simplify the matrix. You know, later on we'll look at how we could do that manually, but for now we just know that a matrix would take care of this. But in order to solve this with a matrix, what do I have to do with all of my equations? Got to get rid of the 4, and they have to be in what form? Standard form, right? So what's that mean? Remind me what that's going to be like. So first of all, we'll clear the fractions by multiplying both sides by 4. Okay. Now what do I have to do with those equations to put them into standard form? So there's my 4 equations. What's that mean? Get those Chromebooks closed. I know you guys are dying to get we'll be done with this in just a few minutes, and then you can plug into it. But this is a really cool application that you're going to want to see. This is something, you'll come back to this in the future, and just trust me, like I've been in these situations where you go to college and everything is new. If you've got some level of prior knowledge to kind of attach your learning to it, man, it's so helpful. Even if you haven't done a lot with it, if you just conceptually understand what's going on. So what do I have to do to put these in standard form? What's that mean? Like with x's and y's and z's, what's standard form mean? Which term has to come first? The x term, and then y, and then z, and then what's on the other side? The constant. Okay, so that's standard form. So which term should probably come first in these equations? T1, then the T2 term, then the T3 term, then the T4 term equals a constant, right? So I just got to move things around to get put the terms in that order. So wouldn't that first one just look like that? Like if I were to move the variables over to the right side and then combine the constants on the left, and then just switch sides, right? That's how we could manipulate that algebraically. Or I could have just subtracted the t term to that side and subtracted the numbers to this side, and I would have just had opposite signs, but it's fine, it doesn't make any difference. I'm just going to do that for all of my equations, all 4 of my equations, and then what would I do to solve this thing? I'm going to take that and, like, what would, if I put this in a matrix, what would the size of my matrix be? 4 by 5. It's got to always be, right? Because if I've got 4 variables, doesn't that imply I'm always going to have 4 columns on the left side of my equation, right? And then I've got an extra column for the constant on the other side of the equation. Give me 1 second. Hey, Shelby? No. Oh, did I or can I? Oh, I will, absolutely, yeah. Okay, bye. Bye. Mom wants you. Yeah. So, does that make sense? I'm going to have a column for T1, the coefficient of T1, column for the coefficient of T2, T3, T4, and then on the other side I have to have a column for the constant, okay? Make sense? So what's row 1 going to look like then? Zero, good. How come 0? No T3. Okay, good. So there's row 1. Well, actually, hang on. We haven't put it in a matrix form yet. That's what we're doing here. So row 1 looks like that, right? Row 2 is going to look like that, and so on. And then what do I do? What magic do I work on Desmos or on my calculator? Put it in reduced row echelon form, so RREF, and I don't want to do that. And what's that tell us? Yeah. So what's, for example, what is row 1 telling us there? T1. Okay, good. So 1 T1 equals that. There's the temperature at T1. There's the temperature at T2, T3, and T4. So one thing I don't think I mentioned that's kind of handy here is if you look at this last column, what it's really doing is it's just giving you can always just read it vertically. It's just giving you, it's like I took this ordered quadruple and I just turned it vertical, right? So these are the values of the variables in order. All you end up having to do is just kind of twist that thing counterclockwise 90 degrees, and those would be the values of the 4 variables, right? It's always going to be in order like that, okay? Give me thumbs on that. Does that all make sense? Okay. All right, so last thing I'm going to show you here, this is just kind of interesting. Solving linear systems, just so you get some idea why using technology and using matrix methods is so useful here. Solving linear systems gets much more difficult as the size of the system grows. If you're doing relatively small systems, you can just do it algebraically. The function below models the total number of calculations that a person or a computer must make to solve an n by n linear system. Okay, so that means n variables and n equations, right? Look at how this grows. It's pretty crazy. Look at how that thing grows. If you go up here, for example, if you've got a linear system with 14 equations and 14 unknowns, you have to make a minimum of 2,107 calculations or you have to do that many steps to solve that. If you get up to a 20 by 20 system, I mean, you're pushing 6,000 individual algebra steps you'd have to make to solve that thing. It's not a big deal if you're only doing a 2 by 2 system. You only have to do 9 things. Like when you guys solve a 2 by 2 system, you're having to do 9 steps internally in order to solve that. 3 by 3 gets a little bigger. It takes 28 total, right? But it starts to grow pretty rapidly. You can see that that curve is, you know, it's just sloping up more and more steeply. And so when you get up to large numbers, you don't want to do that manually, right? That's where matrix methods are much, much more convenient. So, all right, I'm going to turn you loose, let you work on this stuff, get your questions answered.